when you're ready, Mark.
Okay. Thanks for having me. Yeah, I appreciate it. So let's talk. So when you want to like study or describe an algebra, one of the first things you typically try to do is like write down a basis for it. And similarly, when we study higher representation theory, bases of two-morphism spaces of linear two categories are equally important. More recently, categorified superalgebras have been a topic of interest, and categorified superalgebras are not linear two categories, but they're something called two supercategories, which have a superinterchange law instead of the normal exchange law that you see in a two category. As such, we are interested in finding like methods to find bases of two morphism spaces in two supercategories. In my work with Benjamin Dupont and Aaron Latta, we use rewriting theory. We introduce rewriting theory in the setting of two supercategories and use that to provide tools to find bases of two supercategories. So first, let's talk about rewriting theory. So rewriting theory, it's a theory coming from computer science. It studies presentations of things by generators and oriented relations. Such a presentation is called a rewriting system. Basically, we replace a relation A equals B and we orient it A to B, and this is called a rewriting rule. Sequences of rewriting rules are known as rewriting sequences. Oops. All right. So we can kind of think of a rewriting system as a directed graph, with V being some free thing over like the given generators, and the edges being determined by the rewriting steps or the rewriting rules. So for example, let's describe a rewriting system that presents polynomial ring CXY. So CXY it has generators X and Y. And there's a commutativity relation xy equals yx. So, well, the generators will be x and y, but we can think of the vertices as like we take the free algebra over x and y. So we have like cxy. And then to get the rewriting rule, we just orient to the commutativity relation. So let's just pick xy goes to yx. So this relation determines the edges of this directed graph. And we can see an example of a rewriting sequence here. So we have x squared, y squared. We apply the rewriting rule, xy, xy. We apply the rewriting rule to the first instance of xy. So we get yx squared at y. And then we apply the rewriting rule 2 more times. And then we get to y squared, x squared. So this path in the directed graph in the directed graph is like a rewriting sequence. Let's talk about some important things like definitions, properties of rewriting systems that we'll need for basis results. So first is termination. So a rewriting system terminates if there are no infinite rewriting sequences. A typical strategy to prove termination is to have a way to convert is to show that a rewriting sequence corresponds to a strictly decreasing sequence of natural numbers. Since there are no infinite strictly decreasing sequences of natural numbers, it means that it must there are only finitely many. The rewriting sequence terminates after finitely many steps. So, for example, let's look at the rewriting system from the previous example. Like this example. So let's just say we start at some element, like we have x's and y's, and let's we label each y with the number of x's to the left, and we take this and we keep track of the sum of the labels. So this is a natural number, and applying a rewriting step to this term will decrease this sum by exactly 1. As such, a rewriting sequence starting from the described element, basically it goes to a decreasing sequence like n, n-1, n-2, and eventually it reaches 0, at which point we cannot rewrite it anymore. So that means that the longest rewriting sequence starting at this element is finite. This type of proof is very common to show, is used very commonly to show things are terminating. And yeah, so this rewriting system is terminating. Next, let's talk about normal forms. So a normal form is an element that cannot be rewritten using a rewriting step. If we look at the previous example, like y to the ax to the b is a normal form, as there is no xy anywhere in here. When a rewriting system terminates, every element can be rewritten into a normal form. So, next, we'll talk about branching. So a branching of a rewriting system is a pair of rewriting sequences that start at the same point, that start at the same element. A branching is confluent if there exists rewriting sequences f prime and g prime, such that if we apply f prime to the top branch and g prime to the bottom branch, we reach the same element. And a rewriting system is confluent if every branching is confluent. Checking confluence, you usually don't have to check every branching, especially in the case of terminating rewriting systems. Like there's usually a manageable like family of branchings that you have to check, and that will imply confluence of the whole thing. So now we can define convergence. So this will be the convergence is basically confluent and terminating. This is the property that we're interested in for finding bases. And yeah, this is the one we're looking for. So rewriting in like higher dimensional rewriting for higher dimensional linear categories, like there are tools. It provides tools that construct bases of two morphisms. So, for example, quick side definition, like to understand the actual statement, a monomial is basically a composition of generating two morphisms of a linear two category. And the basis tool that we're interested in is that if we have a convergent rewriting system presenting a linear two category, then the set of monomials in normal form is a basis of two morphisms. This is the result that we're interested in, and we want to apply this result to two super categories. However, I haven't actually defined what a two super category is, so I'm not sure. It's not the most likely that people are that familiar with super categories and stuff, so I figured it'd be worthwhile to talk about what a two super category is. So to start, I'm doing all the time, I'm doing all right. So a superspace. So if you know linear categories, like it's basically we have Z2 graded vector spaces. So a superspace is a Z2 graded vector space. We can define the parity of an element. If it lies in V0, it's parity 0, V1 parity 1, at least by homogeneous elements. There's the notion of an even linear map, which is one that preserves like the parity of, it sends V0 to like, if you have like V0 plus V1 and W0 plus W1, it sends V0 to, it sends parity 0 elements to parity 0 elements and parity 1 elements to parity 1 elements. That's what an even linear map is. And the tensor product of superspaces is a superspace, and we can take tensor products of like linear maps. And superspaces and even linear maps form a monoidal category called S-vect. It's actually a symmetric monoidal category with braiding given by given by like U tensor V goes to like this sign V tensor U. Okay, so now that we have that, we can define a supercategory. So a supercategory is a category enrichment aspect. So our morphism spaces are superspaces, and composition is an even linear map. And a superfunctor is similarly defined, it's just a functor enrichment aspect. Supercategories and superfunctors themselves form a monodal category, which we call S-cat. We have composition in like the tensor product of supercategories is given by, again, we have the sign. This sign actually comes from the symmetric braiding. Like this is where it comes from. Anyways, now that we have the monodal category of supercategories, we can enrich again to define as two supercategories. So two supercategory is a category enriched in S-cat. Again, we have HOM supercategories between pairs of element, between pairs of objects, a composition superfunctor, a horizontal composition superfunctor, and vertical composition. We do not like gluing along, like composing along zero cells and one cells by star zero and or circle zero and circle one. Just, yeah, that's a notation. If you're familiar with like linear two categories, basically, if everything is parity zero, then we get a linear category, a linear two category. So diagrammatically, like the main difference when we're working with like linear two categories and two supercategories is we have superinterchange instead of exchange. This adds a sign to the regular, like to the familiar exchange axioms of a two category. So yeah, diagrammatically, when we move U past V, we add this sign. Whereas before in a two category or a linear two category, there is no sign there. So yeah, in my work with Benjamin DuPont and Aaron Lada, we were able to define, like, we described like rewriting systems and like developed some theory on rewriting systems presenting two supercategories. In particular, the basis result that we're interested in, follows it adapts very naturally, like word for word, to two supercategories. So if C is a two supercategory and is presented by a convergent rewriting system P, then the set of monomials in normal form give the basis of two morphisms that we want. So yeah, now we're gonna, so I'm showing up. All right, I have like 7 minutes. That's good. So now I'm going to talk about the basics of our, so what is a rewriting system presenting a two supercategory? I kind of glossed over this with the linear two categories, but it's very similar. So I'll just talk about our like super rewriting system. So yeah, so first, to present a two supercategory with like generators and oriented relations, we first need to like, what do we need to give, what are the generators? Like, how do we generate a two supercategory? So, I mean, we just need our objects generating morphisms, generating two morphisms. Our set of generating two morphisms will be Z2 graded, and like, it'll have like parity 0, parity 1. And basically this is called like the triple P0, P1, P2 is a two super polygraph. And it basically, we can think about it as presenting a free two supercategory. Like, it's freely generated with objects generating one morphisms and generating two morphisms, given by P0, P1, P2. Now, what is so now we need to talk about like relations. So the relations, a relation A equals B between two morphisms. We want to orient that. And we can think about like orienting like an equality between two cells as a 3 cell. In particular, it's like a 3 morphism with parity, and we can assign it a parity. In particular, we get this a 3-2 superpolygraph is basically the collection we have our generators P0, P1, P2, and our oriented relations P3. So there's we can define another like free 3-2 super category. It's basically like you take the free thing. It's I don't plan to get into the nitty-gritty of that. But anyways, these 3-2 superpolygraphs are the rewriting systems that present like 2 supercategories. And by studying them, we can apply that basis result that we've been talking about. So yeah, let's look at an example. So let's talk about this 3-2 superpolygraph O and H. So we have one object, generating one cell, denoted 1, and we denote like n copies, like composing n copies of 1 as n. We have generating 2 cells, like so there's dot from 1 to 1, and there's crossing from 2 to 2. And we have generating 3 cells, DC, YB, ON1, and ON2. So this presents a 2 supercategory that is associated to the odd-nil Hecke algebra. So if you're familiar with the like diagrammatics of the nil Hecke algebra, the odd-nil Hecke algebra, like these are like basically orienting the relations of this algebra, of the superalgebra. So, okay. And in my work, we show that this superpolygraph is convergent. So to show termination, we did a similar thing as we did with the rewriting system presenting CXY, like the polynomial ring. Like it wasn't. We did something similar, like. And to show confluence, we showed that the necessary branchings were confluent. As an example of a necessary branching, let's look at this one. This branching between DC and ON2. So we start at this picture at the top left. We can see that the looking back at DC and ON2, like the domains for like. We can apply both DC and ON2 to this picture. And like the domains which like the sources of DC and ON2, they like overlap. Overlapping branchings are like, the branchings we need to check are like overlapping branchings. Overlapping branchings of where the rewriting sequences are just one rewriting step. So if we apply DC, we can kill this immediately. DC sends double crossing to 0. So we can kill it immediately, or we can slide a dot down. So if we slide the dot down using ON2, we get the bottom left picture. So now the only thing we can do is apply ON1 to this to the first term of the bottom left picture. So sliding the dot down all the way, we get the bottom right term, the bottom right element. So we can see that we have we have the first term and the second and third terms is canceled. We can then kill the first term by using DC again, and we arrive at the same result as if we had just killed it at the start with DC. So yeah. That's an example of it's called the family of branchings we need to check is called a critical branching, and this is a nice example of one. So yeah, Thus, ONH is convergent, and the monomials of the free 2 supercategory with objects generating 1 morphisms and generating 2 morphisms, like the monomials of that guy in normal form recover a basis of 2 morphisms. This basis of 2 morphisms actually corresponds exactly to the basis of the odd-nil hack algebra, which is known. And yeah, I believe yeah, and thank you for your time. Thank you for your time. This is this is a part of the example I did in my paper, the part of the thing we showed in the paper, but it's a nice concept. It's a nice introduction to the thing. So I thought it'd be worth sharing. All right, thank you.
Thanks, Ebert.